Hi, Professor Herzon. How was your weekend?
Hey, it was good. How are you, Caroline?
I'm doing all right.
Caroline, did you take Intro to Physics last semester?
Yeah, I'm in Intro to Physics 2 this semester.
Did you have Sweeney as your prof?
No.
Okay. Yeah, she I mentioned you to her, and she thought she recognized your name.
Oh, so like she technically like she was the second professor in the class, but I only
That's right.
interacted with her like very briefly. I mean, like I know of her, but like I'm much closer with the kind of other professor in the class.
Yeah, with Simon.
Yeah.
Cool. All right. Let me see here. All right. It's recording. Here we go. All right. Good morning, everyone. Hope everyone had a good weekend. Enjoyed a little bit of the nice weather. Today, we're going to continue with our discussion of E2 eliminations. So this was introduced in the pre-recorded lecture for Friday. So hopefully everyone has had a chance to look at that. And so I'll start with a little bit of review from the key points from that lecture. So the E2 elimination is the 2 stands for bimolecular. So you have 2 molecules that are involved in the rate determining step. And in the case of this reaction, there is only one step. There's one transition state, and that is by definition the rate determining step. And the E, of course, stands for elimination. The general mechanism is shown here. So you have some base coming in and removing a proton. And it's useful to stick with the labeling system that we introduced for the SN2. So if the alpha position is the one directly attached to the leaving group, the beta position is one removed. And so the base comes in, pulls off a beta proton, you kick out X minus. And there's a very, very important stereoelectronic effect in the E2 elimination that I tried to really drill home on the Friday lecture, which is that we want to obtain an anti-periplanar arrangement of the CH bond that we're cleaving and the CX bond. So okay, and the molecular orbital basis for that was that that sigma CH bond is going to donate electron density into sigma star of the CX bond, and that weakens the CX bond and then allows for smooth sort of conversion to the pi bond. And again, it's a derivative of hyperconjugation. It's the same type of orbital interaction. You've got an empty orbital interacting with a filled orbital that's adjacent of the correct symmetry. If you can't obtain the anti-periplanar arrangement, you can do what we call a syn-periplanar elimination. And so a syn-periplanar elimination can occur. The orbital overlap is not as good, and so the activation energy is higher. And so therefore, if you can do an anti-periplanar elimination, that is going to be the favored pathway. But syn does occur. And so let me just give you one quick example to drive home the point. So if we've seen these types of bicyclic systems in the problem sets. If we have this substrate here and we want to do an elimination, if you look at the dihedral angle between HB and X, which would be the nominal anti-elimination, is close to about 90 degrees. So okay. And so for that reason, base will not remove HB. Okay, it's very important that you have coplanar alignment of the CX bond and the CH bond, either syn or anti. Okay, this is very important. And so there's obviously no other protons to do an anti-elimination, but the HA and the HA and the CX bond are approximately coplanar. So okay, and so if you labeled HA and HB, say replace one of them with deuterium, and you did an elimination, the product that you would form from this substrate would be this here with HB still intact, okay? So, so you always need to have the CH bond and the CX bond in the same plane. The anti-alignment is favored, call that anti-periplanar. And if I can't access the anti-periplanar geometry, I can do a syn-periplanar elimination if that's available to me. Okay, but if the CX bond and any of the adjacent CH bonds are 90 degrees, you can't do that elimination. It does not proceed, and this is very important in terms of understanding the direction of elimination and how stable something might be towards elimination. Okay. All right. So this is where it gets a little murky. So SN2 and E2 are in competition with one another. Okay. And as I said in the beginning of this chapter, there's going to be very few, unequivocal rules that we can take away from this. It's a lot of balancing all the factors in the reaction. And so we'll spend a couple minutes talking about the things that tilt a reaction pathway towards an elimination at the expense of substitution. So And so I'll list the three factors that favor E2, and then we'll drill down on each of them. The first one is the extent of branching on the substrate. So if you have alpha or beta branching, that will favor E2. The second one gets back to that sort of caution I gave you, that word of caution I gave you about the basicity and nucleophilicity trends. So here you need to actually separate out nucleophilicity and basicity. So when your reagent is a poor nucleophile, but a strong base, you're going to favor E2. And then the final thing is going to be the reagent size. Okay. And so let's unpack these a little bit. Start with the effects of branching. Okay. So if you consider the following substrate, so we have some sort of alkyl bromide and hydrogen. And normally, if I just draw these lines without anything at the end, that implies a methyl group. But just in this instance, I'm just sort of showing a generic substituent. So at both of those carbons. And so if we take that with acetate, we can then go and measure the degree of substitution versus elimination. So this, of course, is SN2, and this one is going to be E2. Okay. And so people have done this. You know, all of this is known now. There was a time not too long ago, 50 years ago, for example, 60 years ago, when, like, you know, people were trying to just work out these different pathways, and so they studied a lot of this in detail. So if you take a simple primary alkyl bromide, and so let's say ethyl bromide, treat that with acetate, you're going to get exclusively the substitution product. Okay. And that's consistent with what we've learned so far. So we said primary alkyl halides or primary substrates are great for the SN2. We know bromide is a good leaving group, and so we're going to get the substitution. Okay. If you go to a secondary, the same outcome is observed. So you get exclusively substitution and no elimination. And again, we said that secondary substrates are the gray area for SN2. This is sort of, you know, if we just kind of open up, you know, consider the possibilities for a secondary substrate, this is the sort of the best case scenario. So you just have two methyl groups attached to the carbon that bears the leaving group. You can't get any smaller than that for a secondary substrate, and so you can still substitute. But when you start to branch, things get very different. So let me draw this one. Okay, so the one on the bottom there is still a secondary substrate, right? The carbon that the leaving group is attached to is directly attached to two other carbons, but I have beta branching. Okay. And remember when we talked about SN2, we said that we were looking at, we separated alpha and beta substitution. And when we were talking about beta substitution, we were using a primary substrate. And we said, if you take ethyl bromide and iteratively replace each of those beta hydrogens with the methyl group, you slow down the rate of substitution. When you get when you replace with 3 methyl groups, you have what we call a neopentyl system. And those actually, even though they're primary, don't do any substitution reactions. So it's the same sort of scenario here. We're taking a secondary substrate and bulking it up at the beta position. And so the rate of substitution then is going to decrease. But I'm still heating with base. I'm still treating the substrate with base. And so it's going to find something else to do. And what else is it going to do? It's going to eliminate. And so in this case, we're about 11%. Let me go back to black here. 11% substitution and 89% elimination. And then finally, I'm running out of real estate on the bottom. I'll just put it on the right here. If you have a tertiary substrate, that is all elimination. Okay, and again, that's consistent with what we said when we talked about SN2. We do not do SN2 reactions at tertiary substrates. They're just too slow, and so the system will eventually start doing the elimination. Okay. The second thing relates to nucleophilicity versus basicity. Okay, and this is, we said in that initial description of SN2 that when you have the same atom attacking, you can typically say that the more basic sort of variant of that atom is going to be a better nucleophile. And so, hydronium or water is or acetate is a better nucleophile than water, and alkoxides are better nucleophiles than acetate because we're increasing the basicity. But when you get to secondary substrates, that's very clear for primary. When you get to secondary, again, it gets murky. And so you really need to separate the basicity and the ideas of basicity and nucleophilicity. So if I take isopropyl bromide and treat that with acetate, we saw this on the last slide, you get exclusively substitution. And none of the elimination product. So 0%, 100%. Okay. And the pKa of the conjugate acid of acetate is acetic acid, and so the pKa is 4.72. All right, Ca for conjugate acid. Okay. If you go to a oxygen-based reagent that's more basic, like an alkoxide, now you get a mixture of products. And so the substitution product forms, but only to the tune of about 45%. And then the elimination product is actually slightly favored at 55%. Okay. And the pKa here of the conjugate acid, which would be ethanol, is about 17. Okay. So it's very important. Let me just pause for a second and iterate. this point. So for primary substrates, when you have the same atom, you're looking at a reagent and you're asking if it's going to behave as a base or a nucleophile, right? When you have a primary substrate and you've got the same reacting atom, it's almost always going to be a nucleophile, unless it gets really big, which I'll come to in a second. When you have secondary, and the stronger nucleophile is going to be the more basic oxyanion. When you have secondary substrates, this is where you need to decouple nucleophilicity and pKa, okay? And so in this case, if you look at the bottom equation, alkoxide is not, a better nucleophile. We're getting more of the elimination product, right? And so as your pKa of the conjugate acid increases, becomes more positive, the elimination pathway starts to predominate, okay? And so I know it's like, it may seem apparently, contradictory, but, the important point is when we were talking about the primary substrates and we were saying what's a good nucleophile, what's a bad nucleophile, there was a correlation with pKa. And so we could just use pKa to get us to the right answer. But with secondary, that correlation breaks down. And so you need to sort of put that aside and think about it from the standpoint of, okay, which reagent's going to be the more basic? And if you remember that in the E2 elimination, that is an acid-base reaction. We haven't, you don't really think of CH bonds as being Bronsted acids, but that is in fact what we're doing. We're transferring a proton. And so stronger bases are going to favor these acid-base pathways, okay? And then the final one is the sterics, which I just alluded to. So sterics, or, AKA size of your reagent. Okay, and so if you take a simple primary alkyl bromide and treat that with ethoxide, you're going to get mostly the substitution product. And a little bit of the elimination product. So this is about 88% and this is about 12%. Okay. But if you make that reagent bigger, so let's say we go to T-butoxide, okay, then we got a problem, or we get a different outcome. Okay, so in this case, we only get a trace amount of the substitution product. This is about 5%. And the elimination product is about 95%. Okay. And so what's going on here? So it's a primary substrate. So displacements should be good, but I'm sort of going to an extreme with my reagent. I'm making it very big as big as I can possibly be at the alpha carbon. So if you think about the spatial sort of positions of the carbon and the hydrogen, so we need to get to carbon to do a substitution, and we need to get to hydrogen to do an elimination, right? And if you think about the structure of molecules, carbons are essentially at the core of the molecule. They're sort of like your body, and the hydrogens are on the periphery. They're your appendages, right? And so if I'm a big reagent coming in, it's going to be much easier for me to get to the hydrogens, which are sticking out on the edges of the molecule, versus working my way all the way in to the carbon at the middle, okay? And that's what we're seeing here with the T-butoxide. It's very bulky, and so it's going to have a high propensity to just go for a hydrogen. It's much easier to access. The ethoxide, much smaller, and so it can get in and do the substitution reaction. Okay. All right. Does anyone have any questions on that? So, all right. So, if not, then I just want to say something about regioisomers in the E2 elimination. So, this is also another complication that we need to think about. And so let's say that I have a substrate like this. So I've got an alkyl bromide, and I've got two methyl groups attached at the alpha carbon. And then I'm going to put an ethyl group in at the beta carbon. Okay. Okay. If we label the carbons, so alpha, beta, 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 right? I have two different types of beta protons, right? And so let's call this beta prime just to distinguish it. So the beta prime protons are secondary, and the beta protons are primary. Okay, does everyone see that? And there's more of just the beta protons, okay? And so just like what we just talked about, substitution versus elimination, when I'm thinking about different ways I can eliminate, the size of the base, the size of the reagent is going to be important, okay? And again, we're not going to even consider substitution with this substrate. Why? Because it's tertiary, okay? And we know that we can't do an SN2 on a tertiary substrate. So that makes it easier, but then we have to deal with this issue of having different types of protons to remove, okay? And so if we treat this with base, we can get two products. We can get the more substituted alkene. Okay, so this one derives from removal of a beta prime proton. Okay, and then the other one is this structure here, the less substituted alkene. So I've got terminal double bond. And in this case, I'm just removing H beta. Okay. Is everyone with me? And so if my base is reasonably small, say it's ethoxide, removal of H beta prime is going to be favored. So I'm going to get the more substituted alkene, and I get about 2-to-1 ratio with the less substituted alkene. Okay. And so, why does it proceed down this pathway. It proceeds down this pathway because the more substituted alkene is always the thermodynamic product. It's the one that's more stable. And the base here is relatively small. Okay, so essentially, if we're not worried about the size of the base, the more substituted alkene is going to be favored. It's going to be where the system wants to go. All right. But if we bulk up the base, again, go to T-butoxide. Okay, now it's much bigger, and those beta prime protons are less accessible. So we get about 11% of the more substituted alkene and almost 89% of the less substituted one. Okay, and it's analogous to what we just described in the last section. So the T-butoxide is very big, and before we were distinguishing displacement from elimination. Now we're distinguishing elimination of a hindered proton from elimination of an unhindered proton. And though the elimination of the more hindered proton, beta prime, is inherently thermodynamically favored, I've now got a very big base. And so it's going to have the same problems getting in there and pulling off beta prime. There's just too much other stuff around. And so it's going to go for the more accessible beta protons. Okay. The other sort of caveat, or the other thing worth noting, is that you've got a 3-to-1 ratio of beta to beta prime in terms of the number of possible protons that can be removed. And so there's a statistically, a greater chance that you're going to have a productive collision with those protons. So the point is that the take-home message from this is straightforward. Larger bases are going to always favor more accessible protons. Okay. And let me just write something down here to help you. So when I say a larger base, that's typically for us is always going to be like T-butoxide. Okay. And a small base for us is always going to be like ethoxide or methoxide. Okay. So if you can sort of commit that to memory, that'll help you. All right. All right. Are there any questions on the elimination? All right. So that's basically all the information we want to cover for SN2 and E2, and it's a lot of information, and I know it's very confusing. There's a good summary at the end of the chapter in the book here, and hopefully you'll have more opportunities to flesh this out during section and at the review session. I want to shift gears and talk about the SN1 reaction, okay? And okay, so the SN1 stands for substitution nucleophilic and unimolecular, okay? And so SN1 pathways are going to be limited to tertiary and sometimes secondary substrates. So we said that tertiary substrates never do an SN2, okay? they will, if they're going to do a substitution, they will do an SN1. Okay. Secondary substrates, again, it's a gray area, and you need to consider the reagent and the leaving group. Okay. So I just want to talk about the mechanism of this reaction for the rest of class, and then in the next lecture, we'll go through, again, the same way, looking at the different parameters. Okay. So as an example, you can consider tert-butyl bromide. All right. And if you take this compound and heat it up in methanol, you'll end up replacing the bromide with a methoxy substituent. So okay. And so what I've done is I've come in and substituted Br for O-methyl, okay? And the mass balance in the reaction is product plus HBr. HBr, very strong acid, pKa of -8. And so if you're using methanol as solvent, it'll protonate the methanol. If we assume that, methanol is protonated methanol is about as acidic as hydronium, we're talking about -1.8. So you're talking about a difference of about 6 or 10 to the 6th, favoring that proton transfer. So we draw the sort of the byproducts as this ion pair here. Let's go. There we go. Okay. And all right, so what is the mechanism? So experiment teaches us that it's a first order reaction. So it only depends on the concentration of the substrate. And so the mechanism can't involve the nucleophile in the rate determining step. Okay. Otherwise, you would see it appear in the rate expression. And so what happens is that you first get a unimolecular ionization. So literally, the bromide just pops off and it takes the electrons in that carbon-bromine bond with it when it leaves. So bang, okay? And then what does that generate? That generates an ion pair. Okay. And that, so I have a carbocation, in this case, a tertiary carbocation, right? And so you can remember when we talked about carbocation stability, we said tertiary was the best of the alkyl cations. And that's what I'm making here, so that's okay, right? And bromide, we know it's pretty, HBr is very acidic, Br minus is very stable, so that is okay. And then I'm in methanol solvent, so my methanol is going to come along and trap that carbocation. So we can take a lone pair, have it attack, and what you end up with is essentially the protonated product. Okay. And that protonated product is going to lose that proton to the methanol solvent. So okay, and so that gives you the products, so the neutral product plus protonated methanol and bromide. Okay. And so you might be thinking, why does this last proton transfer occur? They're sort of similar basicity, and that is a true statement. The answer is that You just have to think about the relative concentrations, you know, so the molarity of pure water is 55 molar. So if we assume methanol is the same, you typically run a reaction, you know, 1 molar is a very concentrated reaction. So if we run it at 1 molar, you're talking 55 to 1 product to solvent. And so just based on Le Chatelier's principle, you've got a lot more solvent around. And so the proton's going to end up more over there. Okay. So that's the arrow pushing mechanism for the SN1. What I want to do then is put this on a reaction energy diagram for y'all. So and so we're going to start out over here with our terp-butyl bromide plus methanol. Okay. And in the first step, there'll be that unimolecular ionization. So I'll go up and cleave the CBr bond to make a cation. Plus Br minus, okay, plus methanol. And then in a second step, I'll trap to form my protonated product. Okay, and I'm going to stop there. Obviously, there's a proton transfer to finish the reaction, but this is all that we really care about. Okay, and so, excuse me. In the first step of this reaction, we cleave that CBr bond, make a cation, right? And if you think about the SN2 reaction, we said that in that transition state, I'm breaking the carbon leaving group bond, but I'm also making the carbon nucleophile bond at the same time, okay? And the SN1 is different in the sense that in the first step, the rate determining step, you're only breaking a bond. You don't get any bond formation, okay? And so what that means is that the activation energy for SN1 reactions are almost always going to be much higher than an SN2 pathway. I'm going through, you know, I'm sort of passing through a transition state and then accessing an intermediate where I've simply broken a bond heterolytically without getting any bond, any enthalpy back from forming a bond. Versus the SN2, you have that concerted formation breaking process. And so that ultimately leads to a lower energy pathway. And so we can say that the activation energy, so delta G double dagger for an SN1 is almost always greater than an SN2, okay? No bond formation in the rate determining step, okay? The second thing that I want to point out is that we're making a carbocation, and so that should alert you to potential rearrangements, right? So okay. And so this isn't so much an issue for tertiary substrates because if you're at a tertiary cation, but we said secondary substrates could kind of break either way in terms of how they react. And if you do an SN1 and then it can rearrange to give a tertiary cation, it's gonna go that route, okay? And then the third thing I want to point out relates to stereochemistry, and this is what makes these reactions really fascinating. So we said that for an SN2 reaction, okay, you have to get backside displacement, backside attack. You have to come in from the back on the substrate. And the reason for that is that we need to get overlap of the nucleophile lone pair orbital with sigma star of the carbon leaving group bond, right? And so you always get inversion. For an SN1, we go through a carbocation. What do we know about the structures of carbocations? Yeah, Caroline.
They're more stable the more substituted they are.
Yeah, what about geometry?
They're planar.
Exactly. The carbocations are planar, right? And so I'm going to go to the next slide so I can have a little more room. So proceeds. Proceeds via carbocation. Planar. Okay. And so I can draw that cation. In this case, it's the T-butyl cation. Okay, like that. And my nucleophile can come in and attack on either face of the cation. Okay, and so I can come in, we're doing this in methanol. And I can attack from the bottom. And I can attack from the top. Okay, and so that's one of the big sort of measurable differences between the SN1 and the SN2. So the SN2, you always get inversion of stereochemistry. The SN1, you lose the stereochemical information. Okay, and that there's no chirality to talk about in the product here. But if you had a tertiary substrate that was chiral, so if you had, for example, just make it a little more interesting. If you had a substrate like that, single enantiomer, and you ran the SN1 reaction, you would form the product. But it would be a mixture of enantiomers. And so I've drawn one absolute stereochemistry there, but the plus minus tells me that I've got a racemic mixture. Okay. And so the stereochemical information, if there is such information, is lost in the SN1. Okay. That's a bit of an oversimplification. So it, strictly speaking, it doesn't always go to a perfectly racemic mixture, and we'll touch on that in the next lecture. But the important point is that whereas in the SN2, you faithfully invert the stereochemistry at the reacting carbon, in the SN1, you basically lose it. Okay. And so, yeah, go ahead.
Quick question.
Yeah.
So I'm still kind of confused on what you mean by losing the stereochemical information. Do you mean that yeah, I was gonna say it's not inversion, then what would it What else would it mean?
Racemization. So I go from a single enantiomer. If I start with a single enantiomer of starting material, I'm going to get a racemate in the product. Does that clarify?
Yeah. Thank
Okay. Yeah. All right. So I just want to end with a couple more points. And so the SN1 is a bad reaction. The reason it's a bad reaction is that I don't get any bond forming in the rate determining step. It just, I'm breaking a bond. And we know that molecules don't just fall apart, right? And so it's sort of inherently less favorable than an SN2, okay? So when can I think about, or when do I need to think about the SN1 pathway, all right? There are two important things that you need to look for. So one is tertiary substrate or secondary, but tertiary more often. And then the second one, which is arguably more important, is a non-basic reagent. And by that, we typically are going to mean a neutral alcohol, okay? Okay, and so let's point two, think about it. Methanol is not a great, it's, it doesn't have a negative charge, okay? It doesn't have a lot of propensity to attack a carbon, okay? Methoxide, on the other hand, has a negative charge, much more reactive, and has a lot of propensity to attack a carbon, okay? And so methanol instead, it's almost like, methanol is like so unreactive that to get it to do something, you need to bring something really reactive in proximity. In that case, it's going to be a carbocation. And so if I have a tertiary substrate with methanol, no reaction by an SN2 pathway, but if I ionize, I generate that high energy carbocation, and that's reactive enough to then snap together with the relatively stable methanol, okay? And so we'll unpack this a little bit more on Wednesday. That's all I wanted to say for now. I am unfortunately not going to be able to do office hours here, but if you have questions, you can either email me with the questions, or we can schedule another time to meet, but I'll be back on Wednesday to do the normal office hours, okay? All right, thanks everyone. Hope you have a good week, and I'll see you on Wednesday.